In parts 1 and 2 of this series, we learned how groundwater moves underground and why it does so, and what happens when it reaches the surface in the form of springs, and how it affects the land all around us. In this episode, we're going to dive into the more extreme cases, particularly hot water systems, geysers, hot springs, and such, and the minerals they bring to the surface. I'm Craig the geologist. Come learn about it with me. Now we know springs are just places where the groundwater, the water table, has intersected the surface of the land and where the water is leaking out. But what about some more extreme and unusual cases? Hot springs, for example. Hot water comes issuing out of the earth. But why is that? Well, the water, generally speaking, hot water is less dense than cold water. You get thermal convection currents. You see this every time you boil water on the stove. You can see this in the earth. Hot water tends to rise up and cold water sinks down. And so the rising action of that hot water brings hot water to the surface, and there you get your hot springs. Now, what's heated the water? Well, there can be several things that heat the water. The most obvious one, the one that everyone tends to think of, is magma. And with that, let's hop over and have a look at a couple of magmatic hydrothermal features, that is geyser basins and hot springs. These are places where even at dusk, the wildlife likes to come and pay a visit. Now, first thing you need to know is that when you come to visit these places, it smells awful. You see all that yellow on the ground there? That is precipitated sulfur. There is a huge amount of sulfur dioxide and sulfuric acid in the air, and it gives everything the smell of rotten eggs. It is not a nice smell, but it's just the smell of volcanic hot springs. Now, I don't think I've given you my location yet. I'm actually at Lassen, which is a national park in Northern California. It is an active volcano. It's not actively erupting at the moment, but as you can see, there's definitely some magmatic activity going on there. It's heating this water and creating these thermal features. Now, the hydrothermal area at Lassen is pretty compact. It's not massive like it is in some places like Yellowstone, but there is a lot going on in a small area. I don't recall whether they refer to this patch as a geyser basin. It doesn't have true geysers, but there are hot springs that spatter about, and in some places where it's a bit muddier, they are what you can call mud pots, and I'll discuss that a little bit more detail in just a minute. Let's have a look at Yellowstone here, and let's begin with its most famous feature, Old Faithful. And before I continue, I just want to apologize for the quantity of photos as opposed to video here. These were taken at a time where I thought my future would involve giving lectures in front of big classrooms at a university or college, where I'd be using a slideshow as opposed to YouTube content where I'd be using video. So there's a lot of photos here. Yellowstone is a supervolcano, and I think that's pop science enough that I don't really need to explain what that means. It is an absolutely enormous volcanic feature, and there is a ridiculous amount of magma still just waiting below the surface. And it will erupt one day. Very unlikely to happen during our lifetimes or during the lifetimes of anyone alive or in the generations to follow for the next couple of thousand years. But it is a huge thermal feature. In fact, between 50 and 60% of all the geysers on Earth occur in Yellowstone. Now let's talk for a minute about how water reaches the surface at these thermal features in Yellowstone. Now, in some places, it comes very gently to the surface in bubbling hot springs. The water of these hot springs can be just crystalline in nature. I mean, you see right to the bottom, you have no idea what the depth is because there is no opacity to the water. In other places, you get vibrant rainbow colors that you can't imagine are actually real. You think, oh, you see a photo, it must be Photoshop, and it's not. These colors are caused by thermophilic bacteria. These are bacteria that probably go back to the formation of the Earth, basically. Not that these species are unchanged since the formation of the Earth, but we believe that during Earth's early history, the first life to arise were probably thermophilic bacteria in environments similar to these. Anyway, those thermophilic, and that means heat-loving, bacteria tend to give these thermal features those vibrant colors. While those bacteria can live in there, you cannot, and people are scalded every year when stepping into those features when they discover that that water is just below the boiling point and you're getting third-degree burns real quick. These hot springs can form mineral crusts on their surface that hide water just beneath. And so in many cases, the people who end up getting burned think they're walking on solid ground, and then their foot falls through a thin crust of ground and they literally boil their legs. On a small scale, the water that comes out of these hot springs needs somewhere to go. It doesn't just circulate directly back down underground. And so these hot springs tend to have little rivers that then wind their way to a much larger stream. And that river is cold. It's not heated enough to be noticeable by all these thermal features out there. When hot water comes to the surface gently, we call it a hot spring. And it tends to evoke a picture in our minds of a very gentle, calming place. When the water comes more vigorously to the surface, we tend to call them geysers. I think I understand why it's called spasmodic geyser. Now, geysers can be massive and erupting hundreds of feet in the air, or you can have pockets of geysers like this one where it's just an extremely vigorous hot spring. Way down deep there is a cavern somewhere that is releasing water that is actually above the boiling point, and that water vapor is shooting up and causing these explosive eruptive type events here. So in case you were wondering what's driving all that vigorous activity, it is steam, it's water vapor, because the water was actually boiling beneath the Earth's surface, and that steam shooting up to the top and blowing all the water out. Here we see more of the same, a bit more vigorous, but all from one centralized vent as opposed to a large distribution of what kind of look like prairie dog holes. A tiny percentage of the water in these geysers comes from the magma, but the vast majority is just recycled rainwater. Water makes its way down, it gets heated by the magma down deep and comes back up to the surface and is boiled near the surface, and the steam creates these explosions. Now, for a geyser, you need water to be right at the boiling point, but not significantly above the boiling point. When it goes above the boiling point, all you get is water vapor coming out, and that is what we call a fumarole. A fumarole is basically like a dry geyser. It's just steam exiting the Earth. Fun aside, as a gas geochemist for the Hawaiian Volcanoes Observatory, way back in the day, like multiple decades, I had to sample fumaroles, collecting the gas in the bottles, on a weekly basis. This is where I did it, in the crater of Kilauea. And by the way, this site has been completely destroyed by volcanic activity since then. And so this isn't a place that anyone can visit now. Now, of course, I was the only one allowed to visit there because I was doing it for work, but it just doesn't exist anymore. It's been covered up by lava and exploded, and it's unrecognizable today. These are the fumaroles that I sampled atop Kilauea volcano. Now, most of the gas coming out of here isn't recycled rainwater that's making its way up. Because the magma is so shallow just beneath the surface here, it's almost all volcanic water and volcanic gases coming out. And so I sampled those to get an estimate of the amount of volcanic activity going on just beneath the surface. Honestly, it was a pretty cool job. So it's a hot spring if hot water is calmly coming up. It's a geyser if it's vigorously erupting right at the boiling point. And it's a fumarole if it's well above the boiling point and just pouring out steam. But what do we call it when the water comes out? Well, kind of disgusting. There is another thermal feature called a mud pot, and that can be pretty common as well. What you have in these places is water vigorously coming up, but mixing with a lot of clays and volcanic ash on the way up and coming up as this thick, goopy, nasty mud. And this is actually one of the more common types of thermal features at hydrothermal fields around the world. And by the way, if you hear me using the term hydrothermal a lot, hydro for water, thermal for heat is just a fancy way of saying hot water systems. I should stop talking for a moment though and just listen to the wonderful sounds these mud pots make. Now, what's heated the water? Well, there can be several things that heat the water. The most obvious one, the one that everyone tends to think of, is magma. In volcanic areas, you can have magma heating the water up and bringing it to the surface. But it doesn't have to be the only source. There can be a number of things. For example, when I was working on my PhD, uncompleted, out in Queensland, I was studying the hot springs out there. And the source of the hot water for those hot springs were radioactive granites. Those are granites that had been solid for millions, hundreds of millions of years, but had a large amount of uranium in there and so had become glowing hot down deep. And they had heated the groundwater and were causing hot springs above them. That's the source of the heat. The source of the water tends to be not very exciting or exotic. There can be some water coming out of those granites or coming out of the magma and being incorporated with those hot springs. But generally, it's all rainwater that's filtered down through the earth and got heated up and brought back to the surface. Now, minerals dissolve in water, and as groundwater systems flow, they slowly dissolve some minerals and redeposit other minerals. But generally speaking, that water is generally speaking, that process is sped up dramatically when you introduce heat. When you heat the water up, it tends to dissolve minerals much more quickly in many cases. And when that water cools down, it tends to lose those minerals just as quickly. And that's a major source of mineralization in a lot of parts of the world. A lot of places that don't have thermal waters anymore, but they did at one point in their history. For example, in the Keweenaw, and I have done a lot of videos showing off beautiful minerals from the Keweenaw. Virtually all of those minerals were emplaced by hot water in the millions of years that followed the mid-continent rift. It was just steaming hot water came through and deposited agate in the empty pore spaces, the amygdules of the basalts, or deposited copper metal and silver, and in some cases, very, very tiny amounts of gold. Prehnite, Dadlite, all these minerals all came from hot thermal waters that were flowing through. And there were probably some beautiful minerals on the surface where the hot springs were issuing. And of course, that all gets eroded over time. But what gets preserved is the stuff underground. And that's what we see today, both in the Keweenaw and in places all around the world. Basically, every place with really beautiful mineralization and great things to collect, 9 times out of 10, there was hot water involved. And on that note, let's take a few minutes to discuss the way hot water and cold water moves minerals around. This giant mound is a pretty big hydrothermal feature that is barely active, but has clearly been active for the past several centuries at least. Now, most minerals dissolve more readily at high temperatures and come out of solution when the temperature cools down. And that's our experience with most things in our day-to-day lives as well. There are some exceptions. For example, calcite is a major one. That one dissolves more easily at cold temperatures, and at hot temperatures comes out of solution. And that's a major problem for limescale in your hot water pipes, because cold water with a lot of dissolved calcite comes in, and once it's heated by your hot water system, the calcite comes out on all your pipes. The primary material that makes up these hydrothermal deposits is travertine. And travertine is a calcite-based mineral, so that might seem a little bit backwards based on what I just said. But what happens is the calcite-enriched water comes shooting out of the geyser, comes down, and it evaporates. The water evaporates away and it leaves behind the calcite that builds up these mounds. The size of these deposits are dependent on a lot of factors. The temperature of the water, the chemistry of the water, the volume of water. They can be very small in size, they can be massive, and they can come together to create enormous mounds as they grow into one another. These deposits can even form on lake bottoms and build their way upward until they reach above the surface of the water. Here you see mounds where the hot water came into the lake bottom, deposited sediments around the opening of the vent, and build itself a pipe upwards, isolating itself from the surrounding lake until it rose above the lake surface itself. Now those are mounds surrounding violently erupted geyser water, but at calmer hot springs you get a lot of mineral deposition as well. That hot water comes up, and as it cools, it deposits layer after layer of mineral. Those layers of mineral being deposited tend to form these interesting terrace structures, and these terrace structures are pretty ubiquitous at thermal springs. You find them all over the globe, not just at Yellowstone. Mammoth Hot Springs in Yellowstone is one of my favorite spots in the whole world. You can see that terrace building perfectly where the water issues from the ground here. Just have a look at these beautiful terrace structures. It's amazing what nature can do. All of this material was dissolved by those hot waters at depth and carried up where they exsolved, where they remove themselves from the water either through evaporation and hyperconcentration or through the cooling effect of the water. Nearby, there's another thermal spring that is not associated with Yellowstone. This is Thermopolis, Wyoming, and as you can see from the giant sign made out of rocks on the hillside, it advertises itself as the world's largest mineral hot spring. Now, I did not take a lot of pictures here because it is a swimming facility and we had the afternoon off with my students, and I wasn't going to bring my camera into hot springs and photograph 17 and 18-year-old kids. That's just not something I do. It's not a great habit to have as a teacher. But have a look at this giant platform that's been built up over the centuries, over the millennia by these hot springs there. Thermopolis is a very family-friendly location for a soak and a swim. It's a great spot, a lot of activities there. But my one recommendation would be don't do it the way we did it. Don't go on a 95-degree day because the hot springs are not as refreshing. This is a small volcanic hot spring in Valles Caldera, New Mexico. And here the hot spring actually comes up inside of a very small cave. So it's a very interesting spot. And you can climb around on it and explore and go swimming at this location. Here you can see on a much smaller scale, you still have those exact same terrace structures that you saw at Yellowstone. It's just on a much smaller scale, and it's partially because the water is not nearly as scalding as it is in Yellowstone. Here you can walk around on this and it's very comfortable. Now, it's very easy to see how these deposits form when you're on the surface, but what's going on beneath the surface is a little bit harder to visualize. And this is just going to be a very cursory look. I could teach an entire semester-long class on this and still barely scratch the surface. Down deep, as waters are moving through cracks in the earth, and this process is accelerated if that water is hot, the water is leaching minerals from the surrounding rocks and leaching elements from those minerals, altering those rocks, changing the mineral content of those rocks. As that water rises, it cools, the chemistry changes, the way it alters the rocks changes, and it might go from a system of withdrawing minerals from the rock to a system of depositing minerals in the rock. You might have a place down deep where the rocks are all being dissolved by those mineral waters, but at the surface, you're getting deposits of precious metals. You're getting agate filling amygdals and basalts. You get all sorts of interesting mineralization where it reaches the surface. This photo here, mundane as it may seem, illustrates just that process happening. This is in Chillago, Queensland, very close to a hot spring, but in a spot where the hot waters no longer flow through the rocks, but they once did. And here you see the complex crack network that the water flowed through, and you see that alteration zone illustrated perfectly in rhyolite. I've spent a long time here talking about thermal waters and the way they move minerals around. And the reason for that is that it's a much more dramatic case. Cold water does the same thing, generally speaking, but on a much slower scale. But there is a mineral that you often find on cliff faces that is leached by water running down those faces. And that is manganese oxide. Manganese oxide creates these black channels and these black faces on cliff surfaces, especially on granites and sandstones. And it's actually very common to find all around the world. Here I'm at Huashan, a very famous mountain area. You find a lot of people here. There's no tourist destination you can go to in China that doesn't have about 400,000 visitors on any given day. But here you see exactly the path that the water runs down every day when it rains. It's leaving these black manganese oxide coatings behind. Now in my Great Lakes area here, these are the rocks that we see most often. This is limestone. And with that, we're pausing it here. Please join me in the next episode where we're going to talk about much more normal cases of groundwater flow, particularly in terms of limestone environments, how it results in springs, cave networks, and some of the most spectacular landscapes on our planet. I hope you'll join me for that.